Hello everyone, my name is Martin Braklund, and in this video I will give you a brief summary of the results in the paper Compatibility of Fundamental Matrices for Complete Graphs. This is a joint paper by me and Felix Rydell at KTH. So I'm sure many of you are already familiar with the concept of the fundamental matrix, but essentially it describes the image of two projective cameras. So given two cameras, you get two images, and the fundamental matrix tells you which point in the first image corresponds to which point in the second image. And yeah, one definition is shown here on screen. So given two cameras, you get one fundamental matrix. Given a set of n cameras, you get n choose two fundamental matrices. Now, you can take any 3x3 rank 2 matrix, any fundamental matrix, and you can always find two cameras for which it is the fundamental matrix. However, if you take a larger set of fundamental matrices, they might not come from some set of real cameras in space. If they do, they are called compatible. And the goal of our paper is to give explicit conditions for fundamental matrices to be compatible. Now, some work has already been done on this. Most famous is probably the result in the book by Hartley and Zisman, where they give the conditions for three fundamental matrices to be compatible. So when do three fundamental matrices come from three real cameras? And for the longest time, it seems to have been believed that this condition is the only one. So given the largest set of fundamental matrices, if each triple is compatible, then so is the whole set. This is not true. And in our paper, or you can check our poster, we give an explicit counterexample where we show that this is not true. And it is not true in general either. What is true is that quadruple-wise compatibility is enough. So with three cameras, you get three fundamental matrices. With four cameras, you get six fundamental matrices. And given a large set of fundamental matrices, if you can check each sextuple and show that it is compatible, then the whole set is compatible. So quadruple-wise compatibility is enough to ensure global compatibility. Triple-wise compatibility is only enough in the case where all the cameras lie on one line. So what we really need to find is the conditions for compatibility for four cameras. Now, with four cameras in space, there are really four possible configurations they can have in space. Case one is where no more than three cameras lie in one plane. And then case 2, 3, and 4 they all lie in the same plane. And case one is like the general one, and is the one I will be giving in this video. The paper has all of them. So we define the epipole to be the kernel of the fundamental matrix. We call it as a rank 2, so it has a non-zero kernel. And then we define the epipolar numbers to be this thing here. Now, the triple-wise compatibility conditions given in the Hartley and Zisman book are also in terms of fundamental and epipolar numbers. So ESIJS needs to be 0. That is enough to ensure triple-wise compatibility. To ensure quadruple-wise compatibility, we get this long condition here, that this product needs to be equal to this product. If so, then the set is compatible. We also give similar conditions for the other three cases, but this is like the main one, general case. And yeah, more details and of course the proof of this can be found in the paper. And we will also be holding a poster session, me and Felix. So feel free to drop by there to ask us any questions that you might have. So yeah, that's all. And I hope to see you all there.